So today I want to take a few steps back and talk a little bit about mathematical notation. Now, in particular, I want to talk about the difference between mathematical notation and physical quantities that you find in a physics equation. This, I believe, is the source of the problem, and as I've been saying all along, the problem is with the language. And in particular, the problem is with the symbolic language of mathematics. So it is my opinion that the symbolic language is the source of the bug that I talk about in some of my other videos. Okay, so you need to understand the symbolic language in order to understand what I'm talking about in terms of unit analysis. So this is not the bug. This is a mathematical expression. It is a symbolic representation. It is a symbolic way of representing this. So these two symbolic expressions, these are exactly the same. This and this are equal. They are literally and mathematically equal to each other. They are just different ways of saying the same thing. So here, for example, 3 to the power of minus 1 is equal to 1/3. So this is not different than this. This is a different way of expressing this. This looks different than this. This might look prettier in a paper. For example, you might want to write this instead of this in a paper, and there's nothing wrong with that. This is not the bug. This is perfectly fine in a mathematical formula. In the body of an equation, you might have a variable to the power of minus 1, and it is going to be equal to 1 over that variable or constant or whatever it is you are talking about. In a mathematical expression, in the body of an equation, this is perfectly fine. But the problem comes in when you do this. Okay, this, in my opinion, is the bug. This is fine. Here we have a problem. Now, this might not look like a problem right off the top. This looks like it is mathematically sound, okay? It looks like, so by convention, historically and by convention, the unit of frequency, the hertz, was assigned the units of the inverse of time, or second to the power of minus 1. This is just a mathematical expression. Okay, this is just a symbol. This is just a symbolic representation of what this is supposed to mean. Okay, and so traditionally, this unit here is per second. Okay, it is per second, and so when you see this unit here and you see it assigned to a frequency term, you read this as per second. So to explain the problem, I'm going to use the Planck's energy equation, and I'm just going to use the standard notation. So the units of Planck's constant in the standard language is joule times second. They refer to that as an action constant, and the units of frequency are per second. Okay, are per second. Now I want you to keep in mind that I always put units in square brackets. So whenever you see something in square brackets, it means I'm doing unit analysis. So in this screen here where I said not the bug, here I'm not doing unit analysis. Here the S's are just variables that you could plug any number into, such as I did with the numerical value of 3. Okay, so this outside of the unit section, this is just a mathematical formula. But inside the unit section, we have to be a little more diligent. And so to explain what I mean by this, I'm going to use the analogy of a cake. Okay, I'm going to use the analogy of making a cake. And so I want you to think of this part of the formula. So this is a whole cake, including the recipe and the ingredients and the process. And so this is the cake, the final product. This is the recipe to make the cake. Okay, and these, the unit section, these are the ingredients that we are going to use to follow the recipe to make the cake. Okay, the cake, the recipe is not the cake, and the ingredients are not the recipe or the cake. Okay, we want to make a cake, we have a recipe, and these are the ingredients. Now, in order for me to make this cake, I need to have an accurate list of all the ingredients that I need to make the cake. So as I'm looking at my recipe book, I look at my ingredients and I look at my ingredients and I go, well, I'm not really sure what that is. I've never made this kind of cake before, and I'm not sure what this is. So I have to go digging to find out what this is. And so I discovered that that is equal to this, and I kind of sort of know what this is. And so I replace, in my ingredients list, I replace this with this, because they are mathematically exactly the same thing. So what I want to do next is I just want to focus on the ingredients. Okay, I just want to look at that section because I really want to know what I need to get so I can make my cake. So I can see here, so what I did was I wrote all the ingredients out as clearly as I could. I had to figure out what a J was. And so I figured out that J was kilograms, meters per second, meters per second. So I know I need some kilograms and a couple of meters per second in my recipe to make the cake. So I go to the store and I look for all these ingredients and I look at my list and I check off all the ingredients, and then I get to this one and I say, one what? So my recipe requires one, but I don't know what that is. So back to the drawing board. Now I have to go back to my recipe book and figure out what this means. So I go back home and I open the recipe book and do a little digging and discover that this one actually means one cycle. And so now I have all the ingredients to make my cake. Now I know when I go to the store, I know what I need to get, okay, in order to make, to follow the recipe and make the cake. Everything is shown, nothing is hidden, everything is written out in full. And so we no longer have the symbolic language. We have a language that is in a more readable form. And so this would be something that would be more suitable for a computer program, because you could think of all of these things as variables. But when you look at it this way, when you look at it with these two together, this is the encrypted short form symbolic language of the units of this expression here, of this formula. And this is it written out in full with no tricks, no symbolic language, like no mathematical symbolic language. Okay, everything is written out in full. And every term in this expression has physical meaning. And so this is much easier to understand, in my opinion. This is much easier for anyone to see, to understand, and look at without being a mathematician. So if you're not a mathematician, you can think of these as the ingredients of a recipe to make a cake. So when you look closely at this, if you look more closely at this, you're going to see that there is a problem. Okay, that's why I keep putting the problem up here. The problem is, so if you look at these units, they look like they cancel. So you end up with the units of the joule. So it looks like you have all the ingredients for to solve your problem. But in here, you can clearly see that the units don't match. You can clearly see that these are not going to cancel to give the units of the joule, because you have this extra ingredient in here that isn't canceled by the per cycle on the in somewhere else in this formula. Okay, so somewhere else in here there has to be a per cycle, and I put that per cycle down here somewhere. Now, sometimes I group it with the energy. Sometimes I group it with the energy, units for the joule, units for energy. So sometimes I put the cycle here. We could also put the cycle here, and then we would have the units for the time period. Okay, so there are many ways to interpret this new equation depending on where you put the cycle term. So if I put the cycle term here and then associate this with Planck's constant, then you can interpret Planck's constant as the energy per cycle. Okay, and of course, the frequency term is cycle per second. Okay, those are the units. It's really cycles per second because you're likely going to have more than one cycle. But the units are cycle per second. And so all of the units are visible. All of the units are accessible. And but you get a different interpretation. And so what's missing here, I believe that these units belong to Planck's constant, and these units belong to the frequency term, and this sort of sticking out of the middle of nowhere second term belongs to a previously hidden measure time term, which you can see right here. So Planck's constant, so these units here belong to Planck's constant. These units here belong to the frequency term, and this second term here actually belongs to a previously hidden time variable, because this is the equation of an experiment, and all experiments require time, especially equations that have a frequency term. So whether you believe me or not that a missing time variable belongs in this equation is neither here nor there. Because I know when I write a computer program, if I want to do this experiment for either more than 1 second or less than 1 second, I need to have a time variable in my computer program. Okay, so whether you want to write it or not in this equation, it's neither here nor there to me, but I know that if I want to do an experiment that is greater than 1 second, like 10 seconds, or less than 1 second, like a half a second, I need to have the time variable in this equation. If I want to know what the output of a half a second's worth of energy are, I have to be able to put 0.5 into this equation. And so 0.5 is half of 1 second. That is the measure time variable. So regardless of whether you think we should write this or not, I think, it has to be clear. It has to be clear that if you want to do more than a 1 second or less than a 1 second experiment, that this has to be written, at least write it in your mind. You have to know that there is a time variable there, even when you don't write it. Okay, so I think we should write it. I don't think we should hide anything. I think we should write our units out in full so we don't make this mistake. Okay, because this bug has led to us not being able to notice, okay, because of that bug, it couldn't be noticed that this formula, these ingredients weren't balanced. Okay, so there was an extra cycle here. Okay, we added the extra cycle here, and then I assign this, the second that used to be part of the action constant. I took it out of the action constant and saw where it really belonged, which is this time variable in this equation of the experiment. And then everything balances, everything works out. And when I solve problems, I still get the right answer. Okay, so I don't get a different answer. I get the same answer using different logic. So this is no longer a problem. This is now the solution. Okay, so I found the solution to what I considered to be a problem, and the problem was in the symbolic language and the misunderstanding and misinterpretation of the legacy language, it's the mathematical language. So the implications, I don't think they really understood the implications of doing this, of making the units of hertz per second. So what per second? Is it cycles per second? Is it radians per second? Is it degrees per second? Is it, photons per second? Is it particles per second? Is it charges per second? So what, what are we doing here? Why are we not saying, why aren't we saying what ingredients we're using in our unit analysis? Per second is not enough information. I need to know what per second. Okay, and even cycle per second is very vague. And cycle per second is also extremely vague. We know what a kilogram is. We know what a meter is. We know what a second is. But cycle's a little vague. And so instead of, in terms of light, in terms of this equation, and even in terms of my own particle model, cycle is really wavefront. Okay, so cycles per second are wave fronts per second. So the frequency term is how many wave fronts per second are entering the detector. How many wave fronts per second is an atom generating. Okay, so this is actually more complete to me. I want to know, is it frames per second like it was in my 3D ultrasound analogy, right? Per second, let's go back, per second is not enough information. This, in my opinion, is the bug. The bug.